Okay, so we're reaching the end of this series. One thing we need to do is be able to put integration by parts together with integration with the u-substitution. So let's put these two things together here with an example. The integral of x times the sine of, let's do pi x with respect to x. Okay, so notice that's not just the sine of x anymore. So what do we do with this? All right, well, we're going to have to go through this process, and we're going to have to, let's let u equal x. I think it's clear why we want to do that. Sine of x is kind of neutral as to whether you want to integrate or differentiate it, but x definitely gets simpler when we take the derivative. So du is just dx. But here, when we integrate, remember this is like what we had done recently. We have an extra factor of pi in here. So guess and check is a real nice way to do this. You could let u equal pi x and go through the whole process of using the chain rule, but we know that the antiderivative has to be a negative. I'm going to leave a little space. It has to have a cosine of pi x. But when we go to work our way back, we would have had to multiply by an extra factor of pi. So we need a 1 over pi right here so that when we take the derivative of v, we will find our way back to dv. Oh, and once again, I was careless. I left off the dx right there. Okay, so now this is just using a simple guess and check method because of the extra factor of pi in the argument of the sine. I needed to have a 1 over pi in front to make it all work out. So this is just review the previous videos. If this step here doesn't make sense, you should be able to do that fairly quickly in your head. If you can't, you are allowed to let u equal pi x and keep going from there. Okay, but we don't need to do that. So we can simply write in the answer. We know that x times sine of pi x dx must equal zig. So that's going to be, let's put the negative 1 over pi in front. We could put the x right on top of that, actually. X over pi times the cosine of pi x. So you could put 1 over pi times x or x over pi. That's the uv minus the integral of the zag. So minus negative 1 over pi. So that becomes plus 1 over pi, the integral of cosine of pi x dx. All right, so we can copy that down, negative x over pi, take the first term down, cosine of pi x. And here we have a plus, we can copy the constant. And we're back to where we were before. We have to integrate a cosine, but there's a pi x inside. So we're simply going to get an extra factor of pi in the denominator there. And then the integral of cosine becomes a sine of pi x. And then we tack on a c. Okay, so once again, this is a sort of, we could do it by u-substitution or a quick guess and check. The antiderivative of cosine is a sine of pi x, but we're going to need to divide. If we're taking derivative, we'd have to multiply by an extra factor of pi. So we need to divide by an extra factor of pi to get the answer. So this is the answer. Let's do one more of those. Let's do this one. Let's do x cubed e to the 2x with respect to x. Now notice this is a third power of x, so we're probably going to want to set up a table because we're going to have iterations. In fact, even if you have 2 iterations, it's probably best. Whoops, I'm sorry. This should be u and this should be dv. So x cubed is the first value of u, e to the 2x is the first value of dv. You keep taking derivatives of u. So as I was saying, even if you have to do this with an x squared, the table might be faster than trying to write out 2 iterations. So 3x squared, we can keep on going. This becomes 6x. Then the derivative of that is 6, and then we get down to 0, which tells us we're at the end. Now, you can't just keep writing e to the 2x. Each time you take an antiderivative, you have to have it. Because going back the other way, you would have to multiply by an extra factor of 2. So we need an extra half. So this will be 1/4 e to the 2x. This will be 1/8 e to the 2x, and this will be 1/16 e to the 2x. So that's where the sort of guess and check antiderivative comes in, but you should be able to do that, and that will shorten the process a lot. So by using this table and a quick sort of guess and check on the derivative, the antiderivatives, you can get your answer much more quickly. So plus, minus on the diagonals. So this must equal x cubed with a 1/2 in front, e to the 2x. And then you will subtract, and you'll get minus 3/4 x squared e to the 2x. And then you will add, and you will have 6/8, which is also 3/4. Okay, that was 6/8, but then you'll have x e to the 2x. And then the last one is subtracted. That's minus 6/16 or 3/8, just e to the 2x. Tack on your plus c at the end. You'll notice every term has an e to the 2x in it, so that could be factored out in the answer. So there you go. Let's do one final example that isn't just an integration by parts problem. Okay. Let's do this. This will take us back to a portfolio. Let's take the function y equals e to the negative x over 2, right? And we're going to look at it on the interval from 0 to 2. Okay? Now, there are various things we could do with it. We could find its average value. Oh, this would be interesting. If we want to find the average value, all right, what we would do is we would take, in order to get y average, the denominator would be the area, so that would be e to the negative x over 2 with respect to x from 0 to 2. But remember, the numerator would get an extra factor of x in there. So the integral of the denominator would be a simple substitution problem, or even a quick substitution where you don't have to write it all out. You can sort of guess and check. But the numerator would be an integration by parts problem with a substitution inside of it, okay? But another thing that you can do, this is the thing I want to do here, is actually rotate that area around the y-axis. Whoops, I should probably extend that out a little bit further. So if we rotate about the y-axis, we get a volume. Now we could try to use washers by using sideways rectangles, but you can see there's a trouble spot right here where we'd have two different regions to work with. So rather than that, get rid of that line. Rather than do that, we're going to want to keep vertical rectangles. Whoops, I accidentally had my eraser. I had to put some lines back in here. There's one. Get a red rectangle back in there. This is going to rotate around over here. And hopefully you remember that gives you a cylindrical shell. So if you rotate that around, you'll have a cylindrical shell there. Okay. Now the bottom will always be on the x-axis and the top will always hit the curve, no matter where I put these, rectangles. They're always going to hit The top will always hit the curve and the bottom will always hit the x-axis. So cylindrical shells might work nicely. So if I were going to do that, I should write out what the volume element is. Delta V for a cylindrical shell is 2 pi r h delta x. Write down what r is, what h is. Well, r is simply how far over the rectangle is, how far it is from the y-axis, and how far something is from the y-axis is just x. So all of these rectangles that we would rotate around to form cylinders are x away from the y-axis, right? How tall are they? They are e to the negative x over 2 tall. Okay, so my volume element would be 2 pi x e to the negative x over 2 delta x. I need to turn that into a volume, and that will bring out the 2 pi. We're integrating from 0 to 2 of x times e to the negative x over 2 dx. And this is just like the first moment integral if we were trying to find the average value. This is going to require integration by parts. Okay, once again, with a little substitution in the middle of that. So let's go ahead and do it by parts, okay? Now remember, these limits don't really work when we're doing it by parts, so we have to make a side problem. We have to find out what is the integral of x e to the negative x over 2 with respect to x. What is the antiderivative, right? So we let u equal x. We'll let dv equal e to the negative x over 2. du will be dx. V is the antiderivative of e to the negative x over 2. So we know we'll have an e to the negative x over 2 back again. But we know if we were taking the derivative, we get an extra factor of negative 1/2. So the antiderivative must have an extra factor of negative 2. You can check if that's right by, if you quickly take the derivative of all of that by the chain rule, you will see that you get back to e to the negative x over 2, which means you're correct, all right? Now the answer is the zig minus the zag. So this will equal negative 2x e to the negative x over 2 minus the integral of the zag. So then that's plus, because there's a double negative, e to the negative x over 2 dx plus c. So let's solve that down here. So we can say the integral of x e to the negative x over 2 dx would equal negative 2x e to the negative x over 2. I just copied the first part of this. And then we have to integrate. Oh, and we already know what the integral of that is. It will be minus 2 e to the negative x over 2 plus c. Okay, so now we need to take the antiderivative of this. Or I'm sorry, we need to use this antiderivative in order to get to the answer. Let me just pause for a second and make sure I have everything right before we finish. Yes, I was suspicious I had a small error. I forgot, let me get my red pen out. I forgot about the 2 that was right here. Whoops, that was my eraser. I forgot about this 2 right here. And so that 2 should go right there. And then if I continue down, that would mean that this would be a 4 right here. So this 2 needs to go away and it needs to become a 4. Then that will be correct. All right. Now to figure out the volume, still need to go back. I haven't figured out the volume. It's 2 pi times this whole antiderivative, negative 2x e to the negative x over 2 minus 4 e to the negative x over 2. We can leave off the c because we can pick any antiderivative. Let's pick the one where c is 0 from x equals 0 to 2. So you can see I put the limits back in now, all right, by using the antiderivative and the fundamental theorem of calculus. Now it looks like bad news because of all these negative signs, but in this case, that's not. So when I put in the 2, I'll end up with negative 4e to the negative 1. And when I put it into the second term, I get another minus 4e to the negative 1. Then when I put 0 in, I will end up with 0, and then I'll have minus 4e to the 0. But remember, e to the 0 is not 0, it's 1. So this ends up giving me a volume of 2 pi times the first term is negative 8 divided by e. Negative 8 divided by e to the negative 1 is the same as dividing by e. And the second term becomes plus 4 times 1. So if you look at that, it's 2 pi times the quantity 4 minus 8 over e. That's likely to be written as 2 pi times 4e minus 8 all over e. And we can probably factor out the 4. So that's likely to be written as 8 pi over 8, or just pi. And then we will have, let me make sure I get this right. Actually, hold on one second. Let me get all my thoughts together. We can factor out the 4. Let me just do this in 2 steps. We'll have 8 pi when we factor a 4 out. We'll have that over 8. When we factor a 4 out, we're left with e minus 2. There we go. So the best answer is pi times e minus 2, which is a positive number because e is about 2.7 something, okay? So the area, the volume of this, when we rotate it around, will be that quantity, all right? It's going to be a fairly small volume because this drops down rather quickly, and this would just simply be a height of 1 here. So even though this is going out to a radius of 2, I didn't show that it drops down further than that, okay? So if I take 1 over e, it's going to drop down rather quickly. So it is going to be a small amount of volume, but this would be the answer using cylindrical shells. Often the cylindrical shells, because it introduces a radius of x, often if we go around the y-axis, often integration by parts is the way to go. In your previous packet, you had come across x, l, and x when you were working with cylindrical shells, and we showed in a previous video how to integrate that. Whereas when you did your portfolio, you didn't know how to do that. You simply had to use MATLAB to get the answer. So that wraps up our integration by parts. There are other tricks that come up with integration by parts, but we've covered all the fundamental cases, which are the most likely ones to occur.